All right, thanks everybody. So we have the schedule. We have a couple of the schedule. So if you look at the schedule, the first hour, more or less, we're going to be spending it doing a little bit level setting, giving a little bit of background. What are the goals and expectations? What are we going to be doing? And if we have some, if we finish a little early, we'll start straight into the material, right? So the idea that during this first hour, we're going to talk about the resources, what is there, essentially, machine learning. I think everybody has even a little bit of experience. Some people have more experience, some people have a lot of experience. So everybody has either read a paper, read an article, or taken a course, or worked on it, or played with some software, solved the problem. So more or less at this point, there's a lot of people that most people have an exposure to machine learning, right? So the goal in this this class is to go a little bit deeper, right? To essentially to become a little bit more fluent, essentially in the way of solving problems using machine learning. So we'll elaborate a little bit more about that. I'll also talk about some of the things we're going to be doing in these 3 days, including the lab challenge, right? So you probably all hopefully downloaded or got the tar file with the material, right? The material there essentially has some code that we're going to be looking at. There's some libraries or some programs that we're going to be running and doing some exercises on them. Has this PDF and other PDF that are essentially the syllabus, the handout. And also has the data sets. That's the most important, right? Because in the data sets is what we're going to be playing with. And the data sets, we're going to be working the labs. We're going to be doing the labs. And the data sets is going to be part of we're going to use them to do our challenge. That is, again, I'll talk a little bit more about that, what the challenge is about. All right, and then during, again, this hour, I also talk about the 10 concepts that you probably either learn in college and you forgot about them, or you probably didn't really learn it because nobody talked about it. But I think that are more or less the 10 things that you perhaps should learn, and then we can again level set this class, right? It's very, very simple stuff. Okay, so as I said, so the goal is to become a little bit more fluent in the art or in the task of solving problems using machine learning. So we are engineers, we're software engineers or engineers of some sort. Our goal is to solve problems, right? Maybe at scale, maybe with higher precision, maybe at a certain speed, maybe better than our competitors, maybe with certain particular data. So we all have a particular problem, right? PlaceIQ has a very specific, very interesting problem, very particular data set, and we as engineers have to solve problems. So here, our goal is to become better problem solvers using the tool of machine learning, right? Now, for some people, what that means is reviewing a little bit more in the theory, right? I think that if you look at the theory, right, if you look at the formulas, what are the assumptions of the algorithms, you become a better problem solver with those algorithms. If you know what the constraints and limitations are. For some other people, they need probably more, hands-on exercises, right? Just to see how it feels to actually run the program and see the output and get an intuition, right? For some other people, it's a mixture of both. Some other people would like to hear more details about advanced techniques. Some others is fundamentals. So hopefully, there's going to be a little bit of everything that here compressed into these 3 days, right? But again, ultimately, the common goal, whether you're very advanced or intermediate or just beginning, is to become a better problem solving using machine learning. All right. Yes. Before I continue, in terms of copyrights, you guys have a syllabus, a handout. Just the text there comes from several of the textbooks, right? So I don't claim that to be my original invention, or I didn't discover anything there. So some of them is really just sentences that were copied from textbooks. So I'll talk about which textbooks, which I recommend that you get a copy of them, right? So again, I want to mention that. Okay, so so specifically, right? So how are we going to become better problem solvers, right? So as I said, some of us need a little bit more background and theoretical. Some of us just need a little bit more demystify, right? A little bit the concept of machine learning, or try to see, that using a particular technique for a particular approach just entails, understanding what's behind it and running it, and then what are the boundaries or limits of that approach, right? Review the main techniques and approaches, right? There are not, and then also goal of this class is to take a look at some real world cases, right? So I have in some use case data that are actually, so one of the data sets is actually a very, very tiny problem set that came from PlaceIQ, right? We can talk about other problems that I've encountered in the past. Some of you, as I said, probably in your work have particular problems, and maybe we can discuss them, right? I don't know if any of you brought your data set to work on it, but that's fine. We have plenty of problems to review here, right? And then, as I said, hands-on exploration through lab components, and at the end, hopefully all these will make you, again, a better problem solver using machine learning. Okay, so there are 3 data sets that are in the tar file. And the first one, I'll call it shadow data set. It's, as much as I could, it's obfuscated, but it's actually real data from PlaceIQ from a problem that we're trying to solve. It's very small, it's very simple, but it gives you an idea of what the problems are. Actually, sometimes the problem comes from having a lot of data, and sometimes the problem comes from not having enough data, right? So this is a tiny problem, and it's going to give you a little bit more intuition of overfitting. What can you do when you have a very, very small amount of data, and still certain techniques are very nice to be run, right? But perhaps the assumptions of the technique do not fit the data well, and how can you find that out quickly, and what can you do about it? So that data set is hopefully going to help us take a look at that. The second data set is based on eHarmony, right? That's available on the web, and I think that's a little bit harder because they actually, this is a larger data set. The problem is eHarmonies is matching, right? Whether it's predicting is two individuals are going to be a good match or not. But it's a larger data set, it's obfuscated. They are not telling you what the variables are, and the way the problem is formulated is a little bit more challenging. So that's, I give it a little bit harder level. We will be using it for our lab. And finally, the hardest one is a data set that comes from the census, right? It's essentially a big table of income being predicted on other variables. I think this is the closest to real world because it has many variables that have many possible values. You have to clean it, normalize it, dimensionality reduction, all the munging and all that stuff. And at the end of the day, you end up with a very, very large table, and you have to do the prediction, what are your assumptions in terms of the modeling approach. So that's probably the hardest, right? So when we do the lab, you can I will give you guidelines to what to look at or work on each of these each of these data sets, and then you can choose any problem that you can pick any of the 3 data sets, and again follow that approach, right? And we will have some sort of evaluation or competition at the end. I'll again tell a little bit more about that later. Now, in terms of books, there's a lot of books. One of the big favorite books that gets mentioned over and over again is the Bishop book and the Tom Mitchell's book on machine learning. Personally, I like the machine learning book by Murphy, right? That's my favorite. And a lot of the content of the book, of the course, is based on that book. If you can, again, I recommend you get a copy. The second one is also a very, very good book, and is freely available in the PDF on the web, right? So that should definitely download it. And the third one, touches the topic of kernels into more, focuses in that topic. So, it's a good resource, especially if you think that you are going to continue working on kernels. Okay. Okay. Now, as I said, most everybody has had some experience using doing some sort of being exposed to machine learning, and there are a lot of online courses. I look at some of them. The one I found the most interesting is Andrew Nunks from Stanford. And his lecture notes are very, very good. So, again, I encourage that you, go, if you're interested in going deeper in a particular topic, you can actually, check out the notes or the class. Now, for this particular course, we're going to be looking into 2 papers, again, that are available on the web. They are part of the tar file. When we talk about EM, estimation. We will be looking at that. And we'll talk about logistic regression, not because it's a great explanation of logistic regression, but actually, everybody is a very popular paper to understand and analyze the results of logistic regression, right? Particularly like, is this model better than this other model, right? Is this good enough, right? This model that I just created with logistic regression. Is logistic regression a good approach to solving this problem? So that paper actually follows a very deep way of understanding logistic regression. So those are part of the resources, right, of the class. Okay, now, so during the class, we're going to have some hands-on activities. And essentially, this is what I think we could, one way or another we're going to be using, right? So some of the code that is example, especially for the first data set, the PlaceIQ data set, I have some Python code. Again, it's not the best code in the world, but it's a clear implementation of an algorithm that you can, again, we have the paper, we have the code, we have the data, and we're going to be running experiments, and you're going to be trying to improve it. You can see very easily how, the algorithm is implemented, and, we'll be playing with that. For that, we only need Python. However, as you get more advanced in machine learning using Python, you would like to look at things, at packages like NumPy, SciPy, and scikit-learn, right? Those are very common. We'll probably be using R, Octave for the Gaussian mixture estimation. And as I said, there's some code that for logistic regression is actually, the Python code, and some code for Octave or MATLAB for EM, right? So, okay. Now, as I said, we're going to have, during the course of 3 days, an ongoing exercise. So today we'll spend later on half hour going into, looking at the data. But the idea is that each of you think a little bit and take a look at the data set and pick one. Actually, you can pick any of those 3 or pick a 4th one that is your own data set, right? Now, as I said, each of these data sets are, small, medium, and large, easy, medium, and hard. And so what we're going to have is some sort of a show and tell at the end, very quick. I realize that we are, we cannot do a detailed show and tell, but it's going to be like an express show and tell of 2 minutes each person. And you're going to tell what you did with that data set in these 3 days, right? We're going to have time here to work on it. So probably just spending a couple of hours here in classroom working, interacting with me and the rest of the class should be enough to do something for your show and tell. But if you want to, go home and work on it a little bit further, that's fine. Now, there are 3 categories for our, show and tell. Again, I'll talk about it a little bit more later, but for the first category is the person that advances the most the accuracy of the classifier. I'll give you a benchmark. The code that is currently in Python has a certain accuracy. If the person that advances most on the category A, on the first data set, is going to be the winner of that category. For the second data set is the eHarmony. You guys have to crack the code, right? Even though you don't understand, or we don't understand because they're obfuscated, the variables, the person that essentially gets the best approach, whether it's a kernel or a feature generation or some sort of modeling that creates some sort of direction towards reducing the error rate in classification or matching or best predictor matching wins. So that's going to be the hacker category because you guys are reverse engineering or cracking the eHarmony set. And the third one is the census data set, right? The person that gets any insight there, whether it's predictive or a pie chart or this variable is correlated with that variable or a regression that makes sense for the third data set. And because it involves the most cleaning and munching and big picture kind of thing, that's going to be the data science category. So we have 3 categories, and you can pick any one you want. You can work on it for, again, the time here in the classroom. You can work at it at home, and at the end, we're going to have a show and tell and have essentially we'll vote for the best performance in each of the 3 categories. All right? Okay. So, okay. So let's let me show you this. So I've heard recently some person talking about, the cycle of how do you solve a problem? What are the steps of solving a problem with machine learning, right? And I think that's very tricky because some problems are so complicated that they don't really fit this mold. And some other problems, are too particular, too peculiar, again, to fit this mold too. But I think this is a general good, description of what the steps are when you are solving a problem using machine learning, right? So essentially, the first is, you get your data, you take a look at a sniff at the data, you plot it, you do a scatter to take a look at the variables. You probably start getting suspicious that not all the variables are independent, so perhaps you start thinking in terms of, how are you going to remove the variables that are redundant. Maybe you realize that your data is sparse, that maybe the values are missing, that maybe your data is skewed, right? Some variables or some categories are getting a lot of counts and so on. So the first is you get your data and you analyze the data. Then the second step, typically, you think, well, I'm going to do a back-of-the-envelope analysis. So I'm going to do a classification. I'm going to do a prediction. Perhaps this technique works. Perhaps I'm going to use linear regression or neural networks or support vector machines or things of that sort. But at that point, you start getting ideas of why certain algorithms are going to work or are not going to work. If you have too many variables, perhaps, if you have a naive approach that requires a factorization of a matrix or things like that, you probably are going to think, well, if I don't use a sparse representation of my matrix, there's no way that this thing is going to fit in memory, right? You start thinking, well, if I don't, sample it, there's no way that, in my runtime is going to run fast enough on my Mac. So probably I would need to run it in a bigger machine. So that's the second step. You start thinking, well, maybe I should, maybe it's not going to fit in R, right? I should not use R. So the third is actually a lot of what essentially data science spent time doing, which is essentially is now getting your data and starting putting it in shape to look like a machine learning ready, right? So we're munging, cleaning, joining, generating feature, imputing values, removing outliers, essentially just cleaning it up and getting it ready. After that, a good idea is to start thinking, should I do a dimensionality reduction, right? If I have 40 million products or 100 million features, right, or words, right? And maybe I don't want to use all of them. Maybe I just want to focus on the top 100. Maybe want to do a projection. Maybe I want to do some sort of a transformation. Maybe just want to get the top most frequent or the most discriminant. So you do a dimensionality reduction. Then once you have your data, you have more or less reduced the dimensionality. You start thinking more seriously about the algorithm, right? Maybe does it make sense to use just a linear classifier, right? Perhaps sometimes that's a good idea, as long as perhaps you do introduce some sort of regularization and so on and so forth. Once you have everything in place, then you essentially start learning the model. You learn the model, you prune the variables, you are assessing the performance. Is the system learning? Is the likelihood increasing? Is the error rate in my training data at least reducing? And then once you are comfortable that that's the right direction, you do some sort of optimization, some cross-validation, you benchmark. At the end, hopefully you'll have time to do error analysis. And then the thing moves to production, right? You might have a classifier, a prediction, a matching that is running on real time on a lot of data, and you just train your models in all these steps. Now, so some thoughts that are practical. Most of us are working on projects that follow Agile, right? The methodology, and have Scrums and have 3-week cycles. Personally, sometimes my managers start thinking, oh, gee, maybe we can do all this in 3 weeks, right? So that's, I haven't seen it happening, but what in my experience, essentially, you probably do kind of like a first pass iteration to get some sort of a sense if the algorithm is working, and then during a second and third cycle, you get to improve the model, and then you worry about the productization, right? So again, it's something that it takes time, and then it becomes your job, right? You probably start constantly thinking about how to better clean these features, how to get better features, how to get more data, how to create the pipelines that is constantly going to be feeding you that data and munching that data and things of that sort. So again, some cycles, some thoughts about this cycle in real life. Okay, so show of hands. Take a quick look, and just if I were to interview you today, right? If you came to PlaceIQ and I interview you, and I ask you, can you define this, and this, and this? So